day. Yeah.
And I can do it because I save 1 hour for driving. Instead of driving to school and back, I have 1 hour extra. But no, the SMC got me. SMC conference was really difficult. Did you participate?
But now it's cold in Canada?
Yes, it is fall. Yeah, it is cold. Well, maybe it's 9 degrees Celsius, 10 degrees. I have to check. I can
below or up to 0?
Above, not below. We hardly ever go below 0.
Okay.
Now it's 10 degrees in 12.
Oh, okay.
Yeah. And the evening is going to be 9, 8.
Okay. So
no, we hardly ever get before 9. I think it's time. Maybe.
Yes, we need to start. Yes.
No. We have 3 minutes. We have 3 minutes.
Oh, no, more or less.
Okay. The recording video has started right now.
Thank you for telling us.
2 minutes, we will start the session, right?
Thank you, Felix.
No, thank you to you. Yes. Have you tried to test your test your share screen?
Yes, we did it 5 minutes ago.
Perfect. Thank you.
It worked. So should I also follow the chat in case there are any questions on chat?
Yes, by chat.
Okay, so maybe somebody else can also follow, but I see the chat from the host.
Yes.
And we have 7 participants.
But there are too many other from the social networks.
Oh, I see. So this so this is shared. Okay.
And from the platform, the landing page too. There are too many.
So somebody is going to follow up with questions over there to let me know if there are any questions over there, because I only see the chat here.
Yes, we are going to be checking Facebook and going to make you the questions.
Okay, if that, whatever you want, you can start.
Good evening, everybody. It is an honor for me to present Dr. Ljiljana Trajkovic. She received doctor engineering degree from University of Pristina, Yugoslavia, master science degree in electrical engineering and computer engineering from Syracuse University, New York, and PhD degree in electrical engineering from University of California at Los Angeles. She is currently a professor of the School of Engineering Science at Fraser University, British Columbia, Canada. From 1905 to 1907, she was a National Science Foundation visiting professor at the University of California, Berkeley. She was a research scientist at Bell Communication Research and a member of the technical staff at AT&T Bell Laboratories. Oh, sorry, it's moving. So her research interests include high performance communication networks, control of communication systems, computer-aided circuit analysis and design, and theory of nonlinear circuits and dynamical systems. Dr. Trajkovic served as IEEE Division 10 Delegate Director for years 2019-2020, and served as IEEE Division X Delegate Director-Elect in 2018. She served as the President of the IEEE Systems and Cybernetic Society and the President of IEEE Circuits and System Society, and the chair of the IEEE Technical Committee on Nonlinear Circuits and Systems. She is the chair of the IEEE Circuits and System Society, joint chapter of the Vancouver Victoria sections. She is the general chair of Systematic Cybernetics 2020 and Systematic Cybernetics 2020 workshop on PMI systems that was one day before, and served as general co-chair of technical program chair of many IEEE conferences and workshops. She served as an associate editor of such journals like IEEE Transactions of Circuit Systems Part 1 and Part 2, IEEE Circuit System Magazine, etc. She is a distinguished lecturer of the IEEE Systems Mind and Cybernetic Society for years 2020-2021, and was a distinguished lecturer of the IEEE Circuits and Systems Society. She is a professional member of IEEE HKN and a life fellow of the IEEE. So, please,
thank you very much,
Professor Trajkovic, you can start. Thank you very much for coming.
Thank you for the nice introduction. I'm going to start sharing the screen now. I hope it's okay, right? So yeah. I'll be talking about machine learning techniques specifically for detecting network anomalies, because my research is in communication networks, and for the last decade we are working with real data from real networks. Either we collect the data or we download the data from various sites. Those data are available to the research community, and then we try to apply various machine learning techniques in order to detect anomalies and intrusions. And that's really part of dealing with cybersecurity and all the worms and blackouts or whatever bad things happen in the internet. So I come from the Communication Networks Lab, and I also put a link to my lab because we have a lot of data and a lot of information on my webpage. Everything is publicly available, all the talks and all the papers and the data sets. And I belong with my students to the School of Engineering Science. We are at Fraser University in Vancouver, British Columbia in Canada. Oops, sorry. So this is a roadmap of my talk. I would like to introduce the topic, and I'll talk a lot about data that we collect and about data processing, because that's sometimes a very time-consuming task. And usually it's a task that my students have to do. And then I'll talk about machine learning models in general. And I'm going to address the models that we specifically use in order to detect these anomalies and intrusions. I'll talk about experimental procedure to show you how we do it, and we'll talk in gory details about performance evaluation. And then I'll conclude and I provide some references, because I think it's important if people are interested and new in this field to actually get a feel about what's out there and where should they start first to read. We have a problem moving the slides. So first, I would like you to view internet as a complex network. And sometimes when I give talks, I really talk about complex networks only. So for me, internet is a complex network. There are many other complex networks that we see, both in engineering systems and in systems in nature. So you might have seen complex networks that capture data sets that come from the documents, from evaluating various chemical processes, from bioengineering systems. For me specifically, a complex network is the internet. And this is how it looks like. So this is actually a real view of the internet. It was captured, I believe, in 2015. And I provided also the credits on the bottom where it comes from. So this is a real snapshot of how the internet looks like. Every node is an autonomous system. Autonomous system means it's a network on a university campus or company. So that's actually a network of networks. So for those of you who would like to study graphs, I think it's a very interesting problem, because it's such an interesting connectivity. And if you see that this every node is a network of networks, there is a lot of room for actually trying to understand the connectivity and how the internet evolves over the years. So the colors are very important here, because the colors actually capture the .com domain, .edu domain, .gov domain, And the distance between the nodes, so the length of the link actually refers to the delay. And so I probably post this somewhere on the web so you can actually look at it. So this is from January 15, 2005. So the lines are drawn between nodes. The length indicates a delay. And so they also specify what kind of classes, that's a term in communication networks, does represent. And the bottom is probably the most interesting for you because you can see dark blue is .net, .ca, .us, green is .com and .org, red is .mil and gov and edu. Yellow represents the various countries, Japan and China, Taiwan, Australia. Magenta is also a different set of countries. So, and some of the ASs are actually of unknown origin. So that's about the network that we are trying to understand. And we are trying to understand what are the wrong things that can happen in terms of intrusions and viruses and blackout. And so the techniques that we use are from machine learning. And as I mentioned, we have been doing this for the last decade or so. And machine learning techniques are used to detect network intrusions. And it's really an important topic in cybersecurity. The algorithms have been used to successfully classify network anomalies and intrusions. And what we call anomaly is actually a classification where you can classify a point as an anomalous point. So usually we do a two-way classification, whether the data that we are looking at is anomalous or it's regular, or you might want to say normal. Or sometimes we can do more than two-way classification. We can do a 3- or 4-way classification where we can identify what kind of intrusion it is. So network intrusions employ diverse deep learning algorithms, of course, convolutional neural networks, recurrent neural networks, deep belief networks, autoencoders, and specifically until now, we've concentrated on supervised machine learning algorithms. We worked quite a while ago with support vector machines, but more recently, we work with deep learning networks such as long short-term memory, gated recurrent unit, and very recently with something quite new, broad learning systems. And I'll tell you more about the systems. So these are the analytical tools that we have at our hands in order to try to classify anomalies. The good part of it is really to do the processing of data. And as I mentioned, data are available out there. You don't have to collect it because it's lengthy and expensive process. But there are ripe and route-use data sets that are available to research community for downloads. They have collected data over the last 10 to 15 years. So it's a really nice and rich data set. And you can also see how internet evolved over the history over the last 15 years if you look at certain parameters, especially if you look into the graphs of the internet and how they evolved. NSLKDD is a well-known data set. It originated from University of California in Irvine. It's very much used in image processing, but they also have some data that are of use to us. CCIDS 2017 and 2018 are data from Canadian sources. They are more new, they're newer, 2017 and 18, but they come from a testbed. So what they did, they sort of simulated the intrusions and attacks in a testbed scenario, and data are also available to the research community. WannaCrypt and Moscow Blackout are another intrusions and anomalies that we looked at very recently. So BGP and SLK KDD datasets are used to evaluate anomaly detection and intrusion techniques. BGP, we used it from RIPE, and I also mentioned route views, but we also had some data from a local network because we had a collaboration with the British Columbia network that support universities and major research institutions around Vancouver. So we were able to actually collect our data. And NSL-KDD that I mentioned, it's an improved version of KDD 99, and it was used already in various intrusion detection systems. IDS is abbreviation for intrusion detection system. These are some gory details about 2017 and 18 data sets. And just to give you a feel about when it was collected, you can see it was collected from in March of 2017 and then in February of 2018. So from 3rd of March, it's 3rd of July. Sorry, I know it is 17 and 18. I'm just giving you a feel about, we talk about a couple of days of intrusions. So this is a graph showing the SLAMA data set. And this is from a network research prephysics. So on the left-hand side, we see the graph. This is the number of BGP announcements. BGP stands for Border Gateway Protocol. And we are looking at announcements. That means announcing the routes that are good to be used in order to transfer the data. So these are the dates from January 2023 to January 28. On the horizontal axis at the time, on the vertical axis is the number of these announcements. And so we identified the time where it was known that slammer virus took the internet down. Notice that we take 1 day of the downtime, and we also look at the data 2 days before and 2 days after. So we have 5 days of data. Granularity is every minute. So if you calculate how many minutes in 5 days, we talk about 7,200 data points. And we identify from the resources and from the literature that the internet was down during that time. So this is identified with the class 1, and class 1 means anomaly, class 0 means regular points. And a similar thing was done for the number of announcements of prefixes. So this is just to give you a feel about what data we're talking about. And similar things were done for the WannaCrypt. WannaCrypt was one of the worms. It's more recent because Slama, Code Red 1, and Lambda happened a long time ago. And most likely hackers will not be able to repeat it because system administrators take precaution so it doesn't happen. But they are very innovative. So they always come with new ways in order to take the internet down. And very often you hear about this in the news. So this is a WannaCrypt. It happened more recently. It's actually a ransomware. That means ransomware means that the owner is blackmailed. And if the owner doesn't pay the price, usually in Bitcoins, then the data is corrupted and removed. And many major institutions were actually affected, even some universities. And notice that now we are talking about different period of time. Again, we are going to identify class 1 as anomaly, class 0 as a regular class, and we can see the number of announcements and the number of prefixes over the period of time when we are looking to see the effect of WannaCrypt. It was a ransomware affecting the internet. This is a Moscow blackout. We also got the data. It was very difficult to actually figure out when the blackout happened. So there was a lot of literature search to figure out when it happened, when the transformer in Chigano, close to Moscow, went down, and that took internet down. Quite a few nodes were down because of the failure of the power grid. And so this is what we can see. We can see that during this time, we have a lot of activity, a lot of announcements that are happening. And usually the volume of the activity is identifies that something bad is happening. It's indication that there is something wrong in the internet. And you can see the spikes, for example, in terms of announcements and in terms of prefixes. So just to give you a graphical view about the data that we're actually trying to analyze. As I mentioned, we look at the days of the attack, and for all BGP anomalies such as Slama, Code Red 1, and IMDA, usually the attack was lasting 1 day. I think one of them lasted more than that. And we take the 2 days before and 2 days after. And then we look at the various features. And BGP update messages have 37 numerical features that we extracted. So the feature extraction is important. And then we have to decide about how to evaluate machine learning algorithms, how to separate the data into data for training and data for testing. And so for our case that I'm going to present you, usually 60% of data used for training and 40% for testing gave us the best results. The rule of the thumb is usually 80-20, and we experimented with that also, but the data performance evaluation data I'm going to show you refers to the using 60% of the data for training and 40% for testing. Just some gory details about events. As I mentioned, there are 2 sites, collection sites, RIPE and route views. RIPE collection site is located in Europe, and a route views is located in Oregon. And they have been collecting data over the last 15 years or more. And the data are available on the web. And so we talk about what I plotted here, it's just a snapshot of Slama, WannaCrypt, and Moscow blackout. We talk about the duration of the data that are regular, the anomaly, and you can see some of them really lasted quite a long time, like one trip we're talking about 5,760 minutes. This is what we use for training. This is what we use for test. And these are indication of the collection site. As I mentioned, SLAMA happened a long time ago. It was from 2003. And this is why we were interested to get newer data. VannaCrypt happened in 2017. Moscow blackout happened in 2005. The collection from RIPE and route use is different, even though the collection is from the same network. Both of the sites are collecting actually activities in the internet. And as I mentioned, one site, RIPE, is located in Europe, and the other site is located in North America. And we were trying also to see what is the difference. Do we really see a big difference between data that are collected from two different sites? Because the collection is from the same internet. Now about the images, the NSL KDD data set, we talk about two data sets, KDD train for training and KDD test plus for testing. We also looked at a very small data set called test -21, because it turned out that this test is very difficult. And so we wanted to see how our approach plays with that data set. So now we talk about 67,000 regular data points. And then we can also identify what kind of worms and attacks there were. DOS stands for denial of service. U2R is another attack. It's user to router, router to link, and there are some probes. And in total, we now talk about quite large data set that's supposed to be analyzed. So this is about NSL KDD. For 2017 and 18 data set, we can see that we can actually now talk about brute force, heartbleed, web attack, infiltration, botnet, variety of worms and attacks and intrusions that affected the internet. DOS stands for the denial of service attack. So they even have the names for variety of attacks. And we looked at the Wednesday of 2017 of the date when we collected. And of course, distributed denial of service attack. And that's usually very common. Okay? And in our data set, that happened on Friday afternoon. These numbers of just to give you a feel that we are talking about more than 500,000 valid flows on Monday, right? So just to give you a feel about the size of the data sets that we talk about. For 2018, as they say, the plot thickens. You can see that we have a variety of attacks that are now happening. So a year later, as I mentioned, people who are attacking the internet are very resourceful, and they come up with various ways to take the internet down. And so in 2018, a new kid on the block came, as I say, so you can see a variety of attacks. So these are all the names that are given to various worms and attacks and intrusions. And on the right-hand side in the column, you can see the total number. Now we are talking about over 1 million data points that are available for analysis. So that's about the data. And the data processing, as I mentioned, takes time. Luckily for research community, the data are available because, as I mentioned, collecting data from real deployed networks with the users, it's very difficult. It's also subject to privacy. So for example, for us to collect data from VCNet, it took us a year to get a permission and to assure everybody that we will not see personal data. So that's why it's so great that these data are available to research community for people who are interested to do this kind of analysis. So you don't have to collect your own data sets. About deep learning, as I mentioned, we are going to talk about the multi-layer recurrent neural networks. And so these are the network that we use. So on the left-hand side, you can see the input layer, recurrent neural network layer. We have 3 fully connected layers, and finally the output layer. So on the top, we are showing the size of the network that we use. So for example, in order to do the analysis of BGP data sets, we use 37 recurrent neural networks. For NSL KDD, we use 109. But in both cases, we use 80, 32, and 16 fully connected hidden nodes. So that's the structure that we have been using in order to do performance. As I mentioned, I'm not going to talk about naive Bayes and SVM and other methods that we use in the past. because more recently we are using long short-term memory. So this is a nice graph that shows you repeating module for the LSTM neural network. So this is the previous time point, current time point, and the output. So these are the cells that are stacked. Then we have on the bottom the general LSTM input layer. It goes through the stack of cells. And finally, we have on the top LSTM output layer. You can see different structures inside. And just as I usually tell my students, please look at the math. This is to show you that there is a very nice mathematical theory behind, and sometimes we forget about it. So these are the mathematical expressions that actually evaluate the data. And so the output of the forget gate f of t is calculated like this. The input gate and the output gate. Sigma is a logistic sigmoid function. We have various weight matrices. X of t is a current input vector. ht minus 1 is the previous output vector. And we also have some bias vectors. I'm going to try to go back just to show you that the equations that I'm showing you actually capture the variables and the parameters that you see on this, indicated in this cell. For example, this is the output vector, previous time and current time. Now the output of the input gate actually decides if the information is going to be stored in the cell state, and this sigmoid function is used to update the information, and cell state in time t is calculated from the previous time and from the current input. Notice that star denotes the element-wise multiplication, and the tan function is used to create a vector for the next cell state. And finally, we get the output of LSTM cell, and this is how it's calculated. Gated recurrent unit, or GRU, it's a simplified version of LSTM, and it actually showed a quite good performance in our studies. So that's the simplified cell, how it looks like, right? Similar idea of stacking the cell in order to create a deep neural network. It depends how many of these cells would you like to use. And it's stacked between the GRE input and output layer. These are the variables and the functions, and I'm going to show you mathematical expressions. So we have the output of the reset gate RT and the update gate ZT at time t. This is how it's calculated, where sigma is a sigmoid function, x of t is the input, ht minus 1 is the previous output of the GRU cell, and we have weight matrices, and we also have bias vectors that's very similar to LSTM cell. This is finally the output of the GRU cell. N of t is calculated with this expression, and we have weight matrices and bias vectors. Now, I also want to mention something quite novel, broad learning system. It was introduced by Philip Chen from, at that time, MICAI University. He moved to South China University of Technology in Guangzhou. And I think some of my colleagues know him quite well. And so I'm going to talk about broad learning system. It was introduced in a conference in January 2007, and I think it was a smaller conference in Shenzhen, but there are also publications now in IEEE transactions on neural networks and learning. And it's quite an interesting approach. Instead of doing deep learning, I think Philip and his team proposed to have something called broad learning system. So this broad learning system, or BLS algorithm, has increments of map features, enhancement nodes, and new input data. So this is how it looks like. So it's broad. So you don't have to go deep in order to create a neural network. And that's quite a nice and interesting approach and a novel approach. You can make it broad. So Z1 through Zn, excuse me, are map features. And you can actually increase the number of map features if you are not happy with the performance. We have enhancements nodes that can be increased. The pink indicates that I'm increasing the number of nodes as I'm doing the processing. And we have input X. These are the functions that I use to calculate the elements. We have output Y. And so these are mapped features. These are enhancements nodes. This is the input. But there is also something else. This is what makes this system incremental. So if I have additional input X sub A, I can actually add additional data without recalculating many of these weights that were done in a previous step. And that makes the algorithm very suitable for large data sets. When you start with a smaller data set, you calculate the performance, you evaluate the performance, and then you want to add additional data. So just this is our original version. There are quite a few flavors of BLS. So we construct matrix A for groups of map features and groups of enhancement nodes, right? These are, we use projection mappings, we use weights and bias parameters. And as I mentioned, we can include additional map features, Zn+1, additional incremental nodes, and additional input nodes. And this is what makes this algorithm, we call it incremental. One thing that made this algorithm very promising and interesting is that it's very fast. So instead of using backpropagation, the algorithm uses Moore-Penrose pseudo-inverse, and that makes it rather fast. And so this is the mathematical expression how we do that. And during the training process, data labels are deduced using calculated weights, map features, and enhancement nodes. I'm just going to give you, I'm giving you in a nutshell the mathematical theory behind BLS. And that was the original vanilla BLS. Later on, there were extensions. One is a radial basis function BLS extension, where the radial basis function is implemented using Gaussian kernel, right? And the weight vectors of the output are deduced from these expressions. As I mentioned, we use pseudo-inverse of H plus. We are not using the backpropagation. So the algorithm is also suitable for doing some cascading, and that adds some depth to the algorithm. So what we see on this graph is that we actually can do cascades of map features. So that's the enhancement of the algorithm. So cascades of map features allow some depth. So it's not only one level on the broad learning system, but it shows that we can add cascades. And these cascades, sometimes you can do hundreds or 200s. It really depends on the performance. One can, so these are the expressions in order to use cascades of map features. In the tables that I'm going to show you related to the results, we call it CFBLS. It stands of cascades of map features for BLS. And the new group of features is created by using a previous group. And this is how they are formulated in terms of mathematical expressions. It's really just for you to get a feel that there is a nice mathematical theory behind. One can also do cascades on enhancement nodes. And you can see on the right-hand side, we have cascades, we have depth. On the left-hand side, we can see map features flat as original BLS. On the right-hand side, we can see that we can add some depth. Not as many layers as in deep learning networks, but tens or hundreds of layers are possible. Enhancement nodes in a cascade for enhancement nodes. We use CEBLS to indicate this is a cascade of enhancement nodes. They are generated from map features. Subsequent nodes are generated from previous nodes, creating a cascade, and the weights and parameters are randomly generated. And one can do even further. So it can do cascades of both map features and enhancement nodes. And this is a structure that I'm showing you. So it's not only broad, but you can add some depth. And of course, it's always incremental because you can add input XA on the bottom. So I'm going to show you now the experimental procedure because we talked about the network that we are trying to analyze. We didn't talk very much of the traffic, but I show you what it looks when the intrusion happens. And then we talked about analysis of tools that we use, machine learning. And so I'm going to show you what we did as experimental procedure. So this is the architecture of the flow chart of the map. So we have data sets on the left-hand side. We divide the data into training and test. And as I mentioned, for many of the tables that I'm showing you, we are going to do 40% of data for training and 20% of test. You can vary this. As I mentioned in the past, it's usually 80-20, in our case it's 60-40. We'll do data processing. That's quite a bit of work. We have to convert categorical features into numerical features. We also sometimes do feature selection, even though in many algorithms that process is hidden. But I want to emphasize how important it is to actually select right features and to understand which features are selected if that's hidden within the algorithm. And of course, normalization. Then we do the training of various machine learning algorithms. And as I mentioned, we are talking about two kinds of deep learning networks, long short-term memory and GRU and BLS. We do 10-fold cross-validation with the parameters. We have a model, and after that we can do classification. That means we can decide whether the point we are looking at, the data point, is anomaly or regular point. So this is a step, right? So I already explained to you the step. And how do we evaluate the models? We evaluate the models based on accuracy and R-score. And we're going to test the recurrent neural network. And inside we do have LSTM and GRU cells, and we are going to do BLS. Features are important, and not all features are equal. So in 2017, we actually extracted 16 most relevant features, and we looked at the evaluated feature importance. You can do that even if you use tools, for example, in MATLAB. You can see that more or less, in this case, features do not vary very much. But we see, for example, that destination port is important, average packet size is important, and this is in decrements, right? So you can see that the value of the features decreases. In 2018, it was more obvious that some features are more important than the others. For example, if you look at the feature importance of a various selected features, and there were many of them in the 2018 dataset, we can see that the forwarded minimum segment size was rather important and relevant. The forwarded initial window size in bytes, this is a TCP term, is also important. And then when you go back to the right-hand side, you can see some of the features are not that important. So you might want to select all the features and try to really train and test your hardware capabilities by using all features. But it turns out that that's not always the best approach. There is a fine balance between how many features you want to use and how much time and CPU resources you want to implement, to devote to this. So the selection of features is rather important. The combination of features is also important. So what you will see on this is a data set from SLAMR. Remember, it happened in 2003. We are looking at the separation of features. So these are the three-dimensional plots. On the vertical axis, we have number of withdrawals. On the horizontal axis, we have average length of AS path between two nodes, ASs. And on this axis, we have number of announcements. And for example, if you deal with these three features, it's obvious that separation is possible. So class 1 or anomaly is represented with red points, class 0 or regular with blue points, and you can see separation is doable, right? More or less, this is the same for the right-hand side. The case was not, for WannaCrypt, it was a more difficult case. Separation into two different classes, we are talking about two-way separation, whether the data points is regular or not, it's a little bit more difficult. So not all the data, not all features are easily separate. For Moscow blackout, maybe we did a little bit better. So the number, this is the same idea. How do we select the features and which features, which combination of features gives me the best separation so that I can actually apply my algorithm successfully and identify regular and anomalous classes. And now, since I believe in reproducible research, I'm going to show you gory details about what are the training parameters that we use. And I'm going to talk about BLS mainly. So these are the four data sets, 3 attacks, and a cell-KDD data set. So these are the numbers of map features we use. We vary the number because we want a good performance. So for example, for classifying NIMDA data set, we needed 500 map features. Groups of map features for SLAMR, we need 25. This is the number of enhancement nodes. In case of incremental learning, we have to worry about steps, how many data points per step, and enhancements nodes per step. So this really would give you information about how to choose the training parameters. These are the training parameters for 2017 and 18 data set. These are just really information for you to see that I hope you can reproduce the results. For incremental BLS, as I mentioned, we are talking about different number of features. We played with different number of features. We wanted to see whether they match or not. And so for 2017 and 18, these are the number of features we use, 32, 64, and 78. And these are the parameters we use in order to train the model. So that's about the models that we use. And I gave you gory details about BLS model, but in our papers, other parameters are also available. And let's look at the performance. The first thing we look at is training time. And this is for RNN models. So you can see that we use Python on CPU and Python on GPU. I'm just only going to show you results for SLAMA and NSLKDD. I'm going to show you 3 models, LSTM, 2, 3, and 4, GRU, 2, 3, and 4. And you can see how long it takes in order to do training. And sometimes we talk about quite a long period of time. And that's for LSTM and GRU. If you look at BLS, and if you look at the training time that's needed for the same data set, we see the order of magnitude improvement. So the BLS is very fast and the performance is comparable. And we use the BLS for Python on CPU and MATLAB. Why is MATLAB doing better? You can see the comparison between 21.53 seconds in order to train SLAMA and 1.36 seconds in MATLAB because MATLAB has optimized code. So you can do even better. Now let's look at the performance. And as I mentioned, we look at the accuracy and F-score. And you can see that we can achieve for these LSTM models that on the left-hand side, accuracy of 94% for quadrant 1. This, you might discard the right is regular. We really didn't have many anomalies there, right? And for F-score for testing was 68.89. So just to give you a feel that we are talking about 70, 80, 90% accuracy for LSTM2. Similar results were obtained for GRU. What I put in colors here are the best performances, right? And some of the performances are not that great. For example, Ninda really gave us a lot of headache because you can see the accuracy is quite low if you do something with the training, and if you train with Ninda and you test it on another data set. Accuracy for BLS is, as I mentioned, quite comparable with everything else. For example, for the 3 worms that attacked internet a long time ago, but this data set is very rich and we still use it. Accuracy for test was 95% and F-score was 66%. So we use actually quadrant 1 in order to train the model, and we test the model on other anomalies. And RFB BLS also achieved comparable performance. Similar idea was with the cascades for features and enhancement nodes and the combination of features and enhancement nodes. So in general, we say that BLS performance is quite comparable, but it's 10 times faster training time. For NSLKDD, these are the accuracy and the F-score for the best models, LSTM4, GRU3, and for cascade of features in BLS. So I'm only showing you the best results. 2017 and 18 data set, similar idea, except in this was a very rich data set. So we could actually look at a very large number of features, way below 37 that we had in SLAMA, Ninda, and quadrant 1. So we played with a variety of features in order to see, does the number of features really matters? It does matter, but not as much as people expect. So on the right-hand side, you can see the training time. Again, this is BLS. We talk about tens of seconds, and in some cases, even smaller than tens of seconds. Okay. And this is incremental BLS. This is when you add the data. So I'm just giving you various flavors of BLS models to show you even with incremental BLS, we do even better because you don't have to recalculate the weights. And this is those because we do pseudo-inverse. We don't do backpropagation. This is just a graph to show you how whatever the tables present. We talk about accuracy and F-score on the left-hand side, right? We talk about BLS and incremental BLS. BLS is blue, incremental BLS is red. On the right-hand side, we have time in seconds. And on the horizontal axis, we see the effect of number of selected features, 16, 32, 64, 78. And as I mentioned, yes, you do better if you use more features, but there is a trade-off. How much time do you want to spend actually doing the classification with all the features? And you can see, as expected, the training time is going to increase if you increase the number of features. And this is for the 2018 data set. It didn't really go as smooth as we expected in terms of training time, but this really depends on the data. So I would like to come closely to the conclusion to sort of tell you what we looked at. We evaluated the performance of deep neural networks using LSTM and GRU. We use deep recurrent neural networks. and we vary a number of hidden layers. BLS models that employ radial basis function, cascades of map features, cascades of enhancement nodes, or even both, and incremental learning will also evaluate. BLS and cascades combinations of features and enhancement nodes achieved comparable performance in terms of accuracy and F-score, much shorter training time because of the wide and deep structure. Because with cascades, you're actually adding depth. So the BLS model consists of small number of hidden layers, and they adjust weights using pseudo-inverse instead of back propagation. They can dynamically update the weights in case of incremental learning. And they better optimize weights due to additional data points for large data set. So if you do incremental, if you have a large data set, they do better optimization. And of course, there is always a price to pay. While increasing the number of map features and enhancement nodes, as well as map groups, leads to better performance, it actually requires additional memory and training time as expected. So I want to show some of the references to give credit what we've done and the data we used. So the data sources come from RIPE and from route views. This is the URL for RIPE. It's public domain. And they also provide the tools. How do you download the data and how do you convert the data from MRT format to the ASCII format that you can use for your algorithms. So this is on top is RIPE. This is route views. This is a location, new location for KDD dataset. KDD 99 was located in Irvine, and then NSL KDD did its improvement because they cleaned the dataset. And these are the two Canadian datasets, 2017 and 18, and they're also publicly available on a request. These are the tools we use. They really comes from my students, Python and PyTorch and Dumpster. BGP C+ tool, that's what we use. We created the tool in order to do some cleaning. So this is a C# tool. And we also updated the data that are now ready for the analysis to the IEEE data port. And we call it a BGP gateway protocol data set. It's not our data, but it's a data that we massaged and we cleaned and we prepared for the machine learning application of machine learning algorithms. The BLS code was also downloaded from a Broad Learning website. That's a website that's maintained by Philip Chen and his students. And we also added some code, but I want to give a credit to the code that we downloaded from that site. Intrusion detection tools have been around for some time. I'm just giving you references to the most important, and not really most important, but something that was important to us. And this is what we use in order, when we started looking into intrusion detection tools. And I put only the surveys that are easy to read and for the people who are interested. Deep learning, these are the major references in deep learning that we use. And finally, the broad learning system. And as I mentioned, it was introduced in 2017. And these are the two main publications that came more recently in IEEE transaction on neural networks and learning, and in 2018 and 19. And I believe there was another publication in 2020. We also do our own work and publish book chapters. The book chapters are easy to read. And so the first book chapter that appeared in Cyber Threat Intelligence by Springer talked about the data that we use, SLAMA, Code Red 1, NIMDA, Moscow blackout. I don't think it talks about WannaCrypt at that time. We also recently means this week, we had the presentations at the International Conference on System and Cybernetics. It was virtually in Toronto. It just happened Monday through Wednesday. And also we had a publication in the IEEE Transactional Circuits and Systems, and presentation was on Monday. It was also virtually held in Seville. This is a list of some recent publications. As I mentioned, everything is available on the web. PDF files can be downloaded. There is no protection. So feel free to download and ask us questions. And then I want to end with this beautiful photo of, it's not a photo, it's a graph of the internet. It's a real capture of internet of 500,000 nodes and 600,000 links. And it comes from CAIDA. They had a very nice project called Walrus Project. And this is a very nice capture of the static graph for internet at one point of time. So thank you very much for listening to my presentation.
Thank you very much, Professor Trajkovic. So for your very interesting and presentation for very important topic. So we have some time for questions. So please, who have questions can write in the chat. So we have two questions. First one, why would GRU be preferable to LSTMs?
Yes, I understand.
Rephrasing my question, in which situation could a GRU be preferable to LSTMs and why, please?
Well, GRU is a simple algorithm. So it's really a simplification of LSTM. So it requires a little bit less CPU, a little bit less time. It has a similar performance. And so this is why we play together both with LSTM and GRU. I cannot specifically answer your question in which specific situations, but both of them perform equally well. It's just that GRU is simpler. It has smaller number of elements in a cell. So it doesn't need as much CPU time as it's needed for LSTM. Is the difference visible? If you measure the time in microseconds, maybe, but we measure our time in seconds. But it's a very interesting question. I might look into the details to see, can we really say that GRU is faster than LSTM? But when you look at the cell, you can see that it's a simpler cell. It has a smaller number of elements inside. So that was the preference, to actually look into GRU and see if we can achieve the same performance with less work. Because some of these algorithms take a long time to be trained. And as you could see from the tables, right? It takes hours and sometimes days. It really depends. And some algorithms you can run on a GPU, some you can't, unless you are going to reprogram and actually write your own code for the GPU. Like Python, I know some of the libraries do not run on GPU. And this is why I was showing in my graphs that we do MATLAB and we do CPU. Can I answer your question, Miguel?
Thank you very much. You want to read again this question? Sorry.
There is if you have, okay, so let's see, where is the question? What is your opinion?
You see, okay. Nice.
I see it on the right hand side. What is your opinion of ensemble methods for the detection of anomalies in networks? Well, we are looking to this. Actually, I would depart from these supervised learning methods. I want to move into more semi-supervised and unsupervised. So I'm working with my students to see how is that going to work, because not all data are labeled. And you can see also that when we're deciding about the period of time, when we say it's anomaly, it's not very easily decided. Like in Moscow blackout, we actually spend a lot of time reading various documents in order to figure out when did it happen. So I'm not sure if I'm answering your question, but yes, I think these are all opportunities. We didn't work with the ensemble methods, but we are looking into this. And as I say, semi-supervised and unsupervised learning, I think is the future, because you don't have labels for many data. And sometimes it's very difficult to label the data, especially for anomalies, worms, attacks, blackouts.
Okay, thank you.
How do you address the data deduplication? Yeah, that's difficult. In our case, when we download data from route views, we do look whether there is overlap, and in order to remove the overlapping points. But I'm going to tell you my experience from another data set that we looked. We collected data from a local network, and it was 911 network. It was a network used by police. And in that case, we actually had the data. We had to look into every data point so to see that there is no overlap. So it really depends from the data point, but you have to look at the data. You also have to have a resident expert to let you know how was the data collected, what in their experience is validity of the data.
Okay. Yes, we have one more question, please.
Okay, so which technique is better for attribute selection? Because 2018, 80 attributes. You mean for features, right? I presume attributes are features. We actually look at the 3D plots, and we plot quite a few of them in order to figure out which features, not only which feature, but which combination of features is going to give me a separation. I'm not going to go back to the presentation, but I think I had 3 slides with each slide had 3-dimensional plots, 2 per page, depending on the anomaly. So you look at this combination to see which feature should I take, because it's not only the feature that's important based on the importance that we calculated, it's also the combination, because depending on that combination, you can see the separation or not. So very often it's a trial and error, and I wish I have mathematical skills in order to give you a more analytical reply, right? But as of now, we just look at the features, and that's why we played with 3 sets of features, like I think 32, 64, 70, right? Because when you have a rich data set, you can have a lot of features. In BGP case, we only have 37 features, but even there we played. We take like 16 features, 37 features. How to select them? You have, it's not necessarily just trial and error, because we also look at the graphs. We also look at these 3-dimensional graphs to see which combination of features is important.
Okay, thank you very much. If we have no more questions in the chat, maybe will be some questions in social networks.
Yeah, you have to read those because I'm...
Yeah, of course. I ask my technical support team, yes. If there is some questions?
No, there are no questions.
No questions. Okay, so if no more questions, we can finish with this part with questions. And we have some certificate for
nice.
excellent presentation, Dr. Trajkovic, the Mexican Society for Artificial Intelligence and the Universidad Panamericana award this certificate to Ljiljana Trajkovic for participating in as a speaker in the keynote entitled Machine Learning Techniques for Detecting Network Anomalies at the 19th Mexican International Conference of Artificial Intelligence, Mexico, October 2020. Thank you very much.
Thank you very much, Professor Ildar.
Thank you.
Thank you. Thank you
Thank you for coming
to
and giving such presentation. Yeah. It's honor for us. Thank you.
Thank you. And maybe next time we see each other face to face.
I hope.
Yeah.
Thank you.
So, but it was very nice visiting you, at least virtually. And thank you for the invitation. It has been an honor and pleasure for me.
Okay, thank you. It's also for us. Thank you.
Thank you.
Goodbye. So we can close